Hello wonderful person, this is Anton, and today we're going to be talking about black holes, and actually quite an interesting and somewhat less explored topic of black holes. We're going to be talking about spinning black holes, and more specifically we're actually going to be discussing the recent paper that managed to measure the spin of a very massive and somewhat distant black hole, or actually a supermassive black hole, technically known as a quasar, located about 3.4 billion light years away from us, and very likely containing 30 billion masses of the Sun. A black hole that you can see pictured right here, known as H1821+643. And in this case, in one of the recent studies, the scientists were able to measure the spin of this black hole, which allowed the scientists to confirm how some of these most massive black holes are very likely produced, and why certain other black holes never really get to become so massive and end up a little bit on the smaller side. For example, the black hole in our own galaxy is nearly 10,000 times less massive, and all of this could be due to the spin of the black hole, at least to some extent. So the spin in this case may play a big role in how much mass a black hole can actually absorb. But that also means that we have to briefly talk about the rotation or the spin of black holes. Now it's actually a little bit difficult to visualize, but as every other object in the universe, black holes also spin. We're not talking about the accretion disk that you see right here, we're talking about the black hole itself, the blackness on the inside. And this spin can actually produce very interesting effects, changing how the black hole affects the environment around it. So here's actually an image of a black hole that's spinning at approximately 99% of the speed of light. It ends up creating effects that would not be possible otherwise. Now, as a result of this, technically there are 4 different types of black holes. We have the rotating and non-rotating black holes, and we have the charged and non-charged black holes. And though in theory all 4 could exist, when it comes to the actual practical discovery of black holes so far, we know that all black holes seem to rotate, at least to some extent, and it's believed that most black holes have at least some charge. In other words, pretty much all black holes out there have at least some rotation and some charge that usually comes to them from various sources that fall into the black hole itself. This is also sometimes known as the transfer of angular momentum, and in this case it also applies to the transfer of charge. And since every single object we've detected so far has at least a little bit of rotation, it's kind of obvious to expect all black holes to have some kind of a rotation as well, even if it's just a small rotation. But we know that some black holes spin super fast. As a matter of fact, many of the smaller black holes, especially the ones that are usually only a few masses of the Sun in mass, spin to the point where they're at their limit, almost at the speed of light. Not so long ago, there was a paper about a very famous black hole known as Cygnus X1. A black hole that's pretty well known because it's basically the first black hole ever discovered. And in this case, it was determined to spin almost at its maximum limit, basically implying that smaller black holes will usually spin at an extremely high speed, which will very likely produce a lot of very unexpected properties. Although obviously at the moment, we're still not really sure what these properties are. But this is very common of many different black holes, and obviously massive black holes spin as well, especially because some of the massive black holes receive so much mass from everywhere. And a lot of mass that falls into these black holes will always contain at least some angular momentum, which will then increase or decrease the spin of the black hole. And so, for example, several papers, like the one you see right here, explore the spin of the famous M87 star black hole. And it's been determined so far that this black hole seems to have a somewhat average spin, not too fast, not too slow, which is sort of expected of a supermassive black hole. This one is also at least 1,000 times more massive than the one located in the Milky Way galaxy, and mostly because of the way that these black holes grow. Generally, when it comes to these really massive black holes, their mass is absorbed from every single angle. Their mass comes from both gas and different stars colliding with the black hole, and today it's believed that they usually grow by absorbing mass in random events and at random times. And so because of this randomness, they would usually acquire an average amount of angular momentum, which means that the rotation would not really increase or decrease too much. It would stay kind of average. Whereas smaller black holes or less massive black holes would very likely mostly absorb their mass from the accretion disk and not so much from anything else. And because of this, and also because the mass seems to come from the same angle at all times, in theory this means that a smaller mass black hole will always have much higher spin, much faster rotation. Or at least that's the theory. But to try to test this, the scientists need to find a way to measure the spin of various black holes. And it just so happens that faster spinning black hole will actually have certain effects around it. And specifically, it's going to allow certain types of mass to come much closer to the center of the black hole than would be otherwise possible. So in other words, because of the spin, it's possible to have a lot more stable orbits around the black hole. It even creates an area known as the ergosphere, which does create some really interesting effects. It's an area where, in theory, it's possible to inject an object and then have this object come out with even more energy than it had originally. In other words, it becomes possible to kind of steal some of the energy from the rotating black hole. A concept that's known as the Penrose process, named after the Nobel Prize winner Roger Penrose, who proposed this years ago. And the thing is, using analog black holes here on planet Earth, specifically using acoustic black holes, the scientists have been able to prove that this indeed exists, and it seems to be possible to extract energy from various black holes as long as they spin and as long as they have the area known as the ergosphere. Meaning that these spinning black holes are actually extremely interesting for a lot of different reasons. One reason being unlimited energy. In theory, it becomes possible to basically extract energy from these black holes, creating a source of free energy. Although in this case the energy comes from the spin of the black hole, meaning that every time you take some energy away, the black hole spins a little bit slower. But nevertheless, it seems to work, at least based on the experiments from planet Earth using acoustic black holes. You can learn more about this in the video right there or in the description below. But this time, using NASA's Chandra X-ray Observatory, the scientists once again were able to measure the spin of a very interesting black hole. The one visible right here. Well, technically it's a quasar. And in this case, this quasar is, as I mentioned before, 30 billion masses of the Sun, one of the most massive black holes known to us. And so as I mentioned before, if the black hole is spinning, it allows some of the particles to come much closer to the center. Because a spinning black hole is going to drag the space around it, allowing the matter to orbit much closer to it than would be otherwise possible. And when the material in the accretion disk comes closer to the black hole, it's going to end up producing certain types of X-rays that would be different if they were produced slightly farther away. This is all because of the gravitational effects from the proximity to the black hole. So basically the X-rays coming from closer are going to be slightly redshifted, whereas the X-rays coming from farther away are going to be less redshifted. Which means that by using X-ray data, it becomes possible to measure the rotation of a certain black hole. And in this case, the scientists determined that H1821+643 spins approximately half as fast as most of the black holes similar to the one located in the Milky Way galaxy. Or in other words, a black hole that's ridiculously massive is going to be spinning much slower than the one located in our own galaxy. Which sort of gives us a little bit of evidence for how we think these black holes grow. So just as I mentioned before, it's believed that more massive black holes will usually have mass coming from everywhere, and because of this they will probably spin slower. That's exactly what the scientists discover in this case. Smaller black holes will have mass mostly coming from the accretion disks, and as a result spin faster because the mass is always coming from the same angle. And that's kind of what we discover with some of the smaller black holes as well. In other words, the study and this observation kind of proves the main ideas the scientists have about the growth of various black holes. Massive black holes will have mass coming from everywhere, grow very fast, and thus acquire much lower angular momentum. Smaller black holes will usually have mass coming from just one angle and will acquire a lot of spin. Although in this case, the massive black holes also get a lot of their mass from the collision with other massive black holes, which would dramatically decrease their overall spin as well, Mostly because it's unlikely that these two black holes are going to be spinning the same way. Which I guess also implies that a lot of these supermassive black holes usually grow through some really violent, very chaotic events, involving a lot of mass coming from every single direction and involving many different collisions. Smaller black holes don't seem to have as much of an excitement, and the one in the middle of our own galaxy very likely experience very few of these events. The Milky Way's black hole, Sagittarius A star, most likely spins much faster than this black hole, and thus also contains a lot less mass. And obviously some of the smallest black holes we've discovered so far spin the fastest. As a matter of fact, as of today, the black hole known as GRS 1915+105 seems to be the fastest spinning black hole we've ever found, rotating at 1150 times per second, as close to theoretical limit as possible, as close to the speed of light. Although in this case this is a relatively small black hole, it's what's known as the stellar mass black hole, approximately 10 to 18 times the mass of the Sun. Either way though, I think it's important to understand that black holes in general do have different types. And in this case, the spinning black holes are actually very different from non-spinning ones, or from the ones that spin slowly. Spinning black holes are usually referred to as the Kerr black holes. But as I mentioned before, spinning black holes can also be charged, and in this case they're known as the Kerr-Newman black holes, and very likely possess very different properties to anything we can even imagine. And that's something we'll discuss in some of the future videos. So, in theory, depending on the rotation and the charge of the black hole, the properties can change quite dramatically, producing very different effects that would not be possible around a simple black hole that doesn't spin much and doesn't have much charge. So one day we might have to stop using the term black hole to describe these different objects, because some of them might actually possess very specific effects, something that we're still trying to investigate and trying to learn more about. Although in this case, this relatively slow spinning supermassive black hole definitively confirms that very massive black holes seem to grow through chaotic events involving collisions with other black holes that very likely make them lose a lot of spin. But it also means that the black hole in the middle of the Milky Way galaxy, Sagittarius A star, could be spinning really fast, and that's something that I would love to hear more about, because at the moment it's not actually known what the spin of the black hole is. And so for all we know, our galaxy might have one of the most unique black holes out there. But we might learn more about this in some of the future videos. And until then, thank you for watching, subscribe, maybe share this video with someone who loves learning about sciences and space, and come back tomorrow to learn something else. Support this channel on Patreon by joining channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.